Alright, let's continue. Example 641. Calculate 675 to the power 307 mod 713. What's happening? It's a huge number, so your calculator cannot, it's beyond the memory of your calculator. So it's a huge number, but now our idea is not to calculate the number itself, but to see when I divide it by 713, how to find the remainder. So here's the idea. You can always, you remember how, now this is more complicated. If you look at those states in the partition, there are some 713 states. And then what? The good news is whenever you get a result, you can always trade it with whoever is in the same state for calculation purposes of the remainder. And that's what we do. As soon as we get a huge number, we go down to the smaller remainder, and then at the end we just add or multiply these remainders and we get the result. Generally, here is the idea, how we can even organize this process even more. And you'll see in a moment why. We'll write first 307 in a binary system. Doesn't have to go that way, but it helps. It's 256 plus 32 plus 16 plus 2 plus 1. If you want, you can do it in ternary system. It doesn't have to be binary. But binary kind of doesn't leave too many holes, and the results are not too big, actually. No, that's more important. And then what? We'll check the following. All right, 675 to the 307 is actually this. 675 to the 256 times 675 to 32 times 675 to 16 times 675 squared, and then times 675. This is according to the properties of multiplication. If you multiply these powers, that's the same as adding the exponents. And now what? We'll calculate on the sides all these powers of 2. So 675 squared is congruent with 18 modulo 713. How did I get to that, by the way? So here it is. Let me show you how you can use calculators to get this, unless you have a feature of a machine that does remainders. So I'll do the following. I'll take 675, I raise it to the square, and I got some numbers. So 675, how did I get this? 675 squared is 455,625. Then I divided that by 713. Divide by 713, and I got 639.025, 245, something like that. 1025, 24, 540. But generally what? This is the quotient, and this is the remainder, but in the fractional form. So I'll do the following. I'll take 675 squared minus 639 times 713. Or you know what I'll do? No. I will take this result from the calculator and I'll subtract 639, and that will give me 0.0252454. So minus 639, and I got this. And this is what? Something over 713. So when I multiply it by 713, it will tell me what the remainder is. Times 713, and I'll get 18. Why? Because generally I know that this represents something over 713. So to recover what something, I just multiply by 713, and I got remainder 18. And then the same way, now what? 675 to the 4th. What's that? That's 675 squared and then squared again. But 675 squared is in the same state as 18, so I can replace that whole arc here. So you can always replace huge number with someone from the same state. So after 675 squared from the previous line to 18, so we know that this is 324. Now 675 to the 8 will be square of the previous one, so I'll just say immediately congruent with less writing, 324 squared. And then I'll do this business. I will take that square, divide by 713. When I get the quotient, remove the quotient. What's left, multiply by 713. And this is congruent. And I just copy the results from the book, from the notes, and that would be 165. Then 675 to the 16. I don't need, oh, I do need 16. I didn't need 8, but I needed to read 16. We want 165 squared, so square the previous line. That's where base 2 comes. So that would be 1675 to 16 would be 165 squared, and that's 131. Then 75 to 32 would be 131 squared, and that's congruent to 49. I'm not writing the index, we all know that it's 713. Then 675 to 64 is congruent with 49 squared, and that's 262. 675 to 128 is congruent with 262 squared, which is congruent with 196. And finally 675 to 256 is congruent with 196 squared, and then using this procedure we get that that's 627. Now what? So I have all the pieces, I don't need all of them. Which one do I need? 256, which is this number. 32, which is this number. I need power 16, which is this number. I need power 2, which is this number. And 675 itself. So generally what? We can assemble them. So we'll say the following. 675 to 307 is congruent with 627 times 49 times 131 times 18 times 675. And then what? If that exceeds your calculator abilities, then what you can do is multiply these to reduce, the same way modulo, multiply these 3 reduce. Either way, actually the way I did, no, just when you do the reduction, it's congruent modulo 713 by 3. Actually, let me try, although you cannot see this probably, or maybe I can actually get this. Let's hope that this is readable. So it's what? 6, usually in our classes we have document camera, I would show this better, times 49 times 131 times 18 times 675, and I'll divide by 713. 627, 49, 131, 18, 675. Oh, we did rounding, and that's what's dangerous sometimes with the calculators. So I have to do it piece by piece. A second and 3. Let me clear this. So about 627 times 49 times 18. I'll take these 3. Divide by 713. Remove 775, multiply by 713, and I got 439. So for these 3, I got 439. So 627, let me make sure that I know which ones I entered because I changed plans. 627, 49, and 18. So these 3 gave me that result. Then I'll go 131 times 675, and I'll divide by 713. Subtract 124, multiply by 713, and I got 13. So I got 13 from these two, I got 439 by those. Now it's easy, 439 times 13 divided by 713. I subtract 8, I'll multiply by 713, and I got 3. This is not equal, it's congruent. So, using nice properties of this relation, we are able to calculate modulo of very high powers using this trick. And then you can see a couple of homework problems of this type. And then here's another progress that we can make in this direction, and this is the theorem that we actually kind of announced when we studied Euclidean algorithm, and that theorem says the following. Theorem 643. It says the following: let A, B belongs to C if GCD of A and B equals N, then there exists U and V from Z such that AU plus BV equals D. Actually, this theorem is related to that problem that was on exam 2, where I asked you set A was actually set like 3Z divisible by 3, set B was 5Z. And I asked you if the set of, and C was AU plus BV, where what, which would be actually, no, C is set of 3U plus 5V, where U and V are integer, and I ask you, is C equals Z? And since 3 and 3 are relatively prime, this theorem says this must happen. And of course, we did it there in a more specific way, but this is generally famous theorem, and it is true. Let me raise this reminder. So what would that be? A real proof would go by induction on the length of the proof. Generally, the whole idea is the following. Let's say that, let's use a proof. If you look at Euclidean algorithm, for A and B, and it looks like this. A equals Q1B plus R1. Then B equals Q2R1 plus R2. And then let's say that Rn, or let me see for indexing, R1 equals Q3R2 plus R3. So if it's Rn here, Q has twice bigger index, so it would be Qn plus 2, Rn plus 1, and let's say there's no remainder. So previous line is what? Rn minus 1 equals Qn plus 1, Rn plus Rn plus 1, and remember the last non-zero remainder, that's your D. So generally what? A real proof would go induction on N, but let me give you a procedure that actually shows what's really happening, and basically that's the induction step. So you go from the bottom up. So first line says the following: D equals, let me make these red, because these are like vectors in a vector space analysis. And these are just coefficients. So D equals, how can I write it? Rn minus 1 minus Qn plus 1 Rn. So look who are my vectors. Rn minus 1 and Rn. Then from the previous line that's missing here actually, then I trade the one with a higher index, this is Rn. So Rn could be traded from the previous line that's missing here. Let me write it there. So what would be the previous line? Rn minus 2 equals Qn Rn minus 1 plus Rn. So here you trade Rn as what? Rn equals Rn minus 2 minus Qn Rn minus 1. So when I traded that, what do I get? Rn minus 1 minus Qn plus 1. Rn could be traded as Rn minus 2 minus Qn Rn minus 1. Never execute multiplication on R's, on those red ones. Do all the calculations with coefficients, but not with vectors. So it's Rn minus 1 minus Qn plus 1 Rn minus 2 and plus Qn plus 1 Qn Rn minus 1. And then these two could be combined, so it would be what? 1 plus Qn plus 1 Qn Rn minus 1 minus Qn plus 1 Rn minus 2. So what happened? Now I have the other members, n minus 1 and n minus 2. Who is younger among them? This guy is younger, he has higher index, so he could be traded using next line, and so on. At the end, when you continue this, at the end you will express everything with the two oldest members, two guys in the beginning of the story, which is A, B. And that's basically a proof. As I said, I could have done it using induction, but I think this is telling you more how things should be done. And let's just do this specific example that actually reports that. So this example says 642. It says the following. Actually 642 will say the following. Find the multiplicative inverse of 43 modulo 660. What? First, what is multiplicative inverse? We wrote it down. Multiplicative inverse modulo 660. So multiplicative inverse means two things should be multiplied to give me 1. But not exactly 1. It says modulo 660, so congruent here is 660. And then multiplicative inverse of a particular number, which one is it? 43. And they want this x, that 43 times x is congruent with 1 modulo 660. Why would we need that? We'll see that in a moment. So the question is, how can we do it? And the second one, how? If we can, how can we do it? First answer is yes. Because 43 is a relatively prime for 660. That's easy to see. And now what we'll do, we'll actually use the construction from a minute ago and do the following. We'll do Euclidean algorithm. So we'll do the following. 660 equals 43, let me do that red. 660 is like a vector. Equals, I divide 660 by 43, I get 15. And I get remainder 15. On the next line, you continue with red ones. 43 equals, that's easy to calculate now, 2 times 15 and plus 13. Now I go 15 equals 1 times 13 and plus 2. And then 13 equals 6 times 2 and plus 1. And that's it. That's the last non-zero remainder because 2 is multiple of 1. So this is GCD from a minute ago. Since they are relatively prime, I'm not surprised that that's 1. So what did we say a minute ago? Now you go backwards and you say the following: 1 equals 13 minus 6 times 2 equals. Now you want 2 is the younger one of those, appeared later. So 2 is now traded. How do you trade 2 from this line? So you read that 2 equals 15 minus 1 times 13. And that's where you trade. 13 minus 6 times 15 minus 1 times 13. Never multiply red numbers, just black ones. So in algebra, it's 13 minus 6 times 15 minus 6 times minus 1 is plus 6. I multiply them, plus 6 times 13. So I get 6 times 13, and 13 is 7 times 13 minus 6 times 15. By the way, I can check that this 91 minus 90 is 1, so it's all good. Now what do we do? Who's younger here? 13. So 13 should be traded here. So what's 13? Is what? 43 minus 2 times 15. And then I trade 7 times 43 minus 2 times 15 and minus 6 times 15. If I multiply, I get 7 times 43 minus 20 times 15. How did I get that? 7 black ones could be multiplied. 7 minus 14 and minus 6 is minus 20. Now what do? I finally trade 15. So 15 is traded as what? 15 equals 660 minus 15 times 43. And when I trade that, I get 7 times 43 minus 20 times 660 minus 15 times 43 should be right. 43. And then if I distribute the black numbers on 43, I'll get minus 20 times minus 15 is 300, 307 times 43 minus 20 times 660. Let me check my calculation. 307, yes. Now what? But how is this answering our question 43 times x is congruent with 1? Look at this. This is the multiple of 660. So if you look modulo 660, that's a 0, because that's in the class of 0. So this is congruent with 0. So generally what we have is the following, that 1 is congruent modulo 660 with 307 times 43. So what is that telling us? That at x that we are looking for, x is 307. So this is how we can find multiplicative inverse for certain module if, of course, our number is relatively prime to that module. This is an important construction for what we'll do in our next few constructions. So it's worth memorizing. It's a famous construction used heavily in algebra, in programming, and in many mathematical constructions.